Since 2000, I developed software to calculate the heat transmission between PCM objects and forced fluid flow. While in the early years mainly airflow was focused, water flow was the main point of the investigations and developments during the last years. Experimental setups were installed to measure the thermal behavior between PCM objects, mainly stored in bulks inside thermal tanks, and the fluid passing the tank. The total amount of stored energy inside latent thermal storage systems is empirically exactly calculatable when PCM data is known according to RAL quality mark 896. Thermal power over time is not calculatable according to unknown streaming pattern inside the thermal storage system and highly instationary heat transmission and conduction in combination with phase change inside the PCM objects. After investigating several approaches, the most exact solution consists of an empirical approach for the heat transmission between fluid and PCM object, mainly influenced by a heat transmission coefficient depending on the fluid velocity, and an additionally numerically approach to implement a dynamical simulation of the heat conduction between the discrete volumes of the discretized PCM objects. The temperature-depending heat storage capacity of each discretized volume element of the PCM objects is programmed in 1 Kelvin steps according to RAL quality mark 896. A one-dimensional discretization of the objects has proven to be sufficiently accurate. Different masses of corresponding layers have adapted exchange surfaces to enable calculable transient heat exchange between individual layers. This approach can be chosen for various PCM objects. In doing so, the different approaches for layer masses and transfer surfaces can be calibrated by using measurements. In the fully version of the software, any storage system, PCM, and object can be created and managed in the database. In the demo version, a predefined number of database entries can be selected. Here, an individual database of self-defined storage system is presented. In the PCM database, the material properties of phase change materials are entered in accordance with RAL quality mark 896. The input data can be graphically represented. In addition to the data for the storage system and PCM discretization data for PCM objects, these can be created following the previously presented principle. In the full version, the program provides import capabilities for measurement values to validate these parameters. After selecting the storage system, PCM, and objects, the program allows for the dynamic simulation of the entire system. 3 simulation cases are implemented in the program. First case is the simulation of a storage system under laboratory conditions. A thermally initialized storage is subjected to a constant flow temperature. The step response enables the determination of the theoretical storage capacity and the possible optimal charging and discharging power. The second simulation variant allows for a time variable control of the storage mass flow. This enables a theoretically constant charging or discharging power of the system. The third variant allows for a realistic simulation of the storage. The program enables the programming of a schedule for thermal power to be delivered or to be absorbed from a secondary system. Simultaneously, a heat or cold source can be defined to regenerate the storage system. In this example, a test storage with a PCM featuring a phase transition at approximately 58 degrees Celsius has been selected. The PCM is implemented in objects of round types of heat cell 180 mm diameter. A step response is simulated. During the simulation, the full version of the program allows for the simultaneously display of real measurement values. This approach enables the validation of PCM discretization parameters for the objects. In this graph, the solid lines correspond to the simulation results and the dotted values represent the measured values from the laboratory. The good agreement between measurement and simulation is evident. It should be noted that the red line does not depict the storage inlet temperature like the measured values, but rather the average temperature of the storage layer at the top end of the storage.